Okay, so we were looking at this, my favorite vector function here last time. That's this one. X is cosine t, y is t to the fourth minus 4t cubed, etc. Z is 0.5 sine 5t. And we were talking about whether these particular functions were real valued or vector functions. And when I say real value or vector, I'm talking about the independent variable or the dependent variable? They're saying dependent. Agree with that? Yeah, so a real valued function, it gives you the output, it determines real values. A vector function, it gives you vectors, right? So this, what kind of function is this? Vector or real valued? Vector. The output of this function, here's t down here. It's changing. Now it's 5 about, so it's negative. Now 0. Now it's 1. Now it's 2. Now it's 3, etc. And for every one of those t values, the parameter, you get a vector. Put those vectors in standard position. Those vectors sweep out a curve, right? So that the coordinates of all those points on the curve are the same as the components of the vector that you got for that t value, right? Okay, so let me just show you some, and then last time we determined all these functions whether they were real valued or vector function. We're not going to go over those again, but let me show you. We'll just pick one here. So here's one of those. Which one of those is this one that I'm showing you now? So is it this purple, denoted by the purple vector? Is this the speed function, the velocity function, the direction of motion function, or the direction of turning function, or acceleration function? So what do you think? Which one? People are saying direction of motion. That's what I'm hearing mostly. Agree with that? And why is that not the velocity function? Magnitude is constant. All it's showing is the direction. Magnitude is staying constant. Okay? Let's go back and look at... Okay? So then what's this one? Which one of those is this? This is velocity, because it's showing direction of motion, but it's changing magnitude according to speed. So, yeah, if this is a particle flying through space, then it would truly be speed. If it were some other function that wasn't position in space, then it would just be how fast is the curve being swept out for changing t, right? So like in the back, the curve gets swept out. Lots of the curve gets swept out for a change in t. And so in the back, that vector is that. And so the velocity, if it's, my function is r of t, what is this function right now? Oh, my favorite. Let's put this. So if I'm showing you, if the red curve represents, and the black vectors represent r of t, then what is this blue vector function relative to r of t? R prime, right? R prime, that's the velocity. So the blue one is r prime, and this is the velocity function. Okay, very good. All right, here's another one. All right, I'm still showing velocity, and now I have another one. It's gold. All right. I can slow this down a little bit, but here it comes. So in front, you can see this nice gold or orange or something. Any thoughts about this? I'm going to take it a little slower here. So I'm going to freeze a moment here at t equals negative 0.74. Here's this orange vector, this new gold vector. All right. Here's t is negative 0.43. Here's t of 0.68. Here is t of 1.16. Seems to be in the same direction as the blue one. Here's t of 1.81. Now it looks like it's orthogonal to the blue one. Here in the back. I know, I think it's really cool too. So here now facing from the back side. So here's the direction, here's the velocity vector, the blue one. The gold one is kind of in the, what is this gold vector?
Acceleration.
Okay. It's acceleration. What's the direction of the acceleration? Is it in the direction of the curve? Is it in the direction of t? You know, t is the direction of r prime, right? That's unit vector in r prime. Is it the direction of t? No. No. Is it the direction of n? Is the direction of turning, right? Which way it's turning? Is it the direction of n? How about now? Is it in the direction of n? It's like in the opposite direction of the velocity. But then what about now? Yeah, so now it's like orthogonal. You sure this is acceleration?
Yes.
Someone said yes, definitively. Well, how do we make sense of that, right? The direction is flying all over the place. Sometimes it points in the direction of t. Sometimes it's pointing in the direction opposite of t. Sometimes it looks like it's pointing in the direction of n. And everything in between, right? So some of you may have some insight into what's going on here. So hold on to that thought. Let's see what happens with the math with this. So yes, this is indeed is the acceleration. And what is that relative to r? So the blue one is r prime. And now my gold one, I even have a gold colored pen. What would it be? R double prime. But notice how the direction is all over the place. Sometimes it's in the opposite direction of the velocity. Sometimes it's right in line with the velocity. Sometimes it seems to be in the direction of n. And then, like I said, everything in between. So we want to make sense of that. So and the mathematics is how we can make sense of that. And then we'll come back to this picture after we've gone through the math of acceleration. We'll come back to this picture and it'll all make sense. Oh, of course. And some of you may have some ideas already. That's good. All right, so we'll hold on to that picture and let's talk about acceleration. It's getting good now. It's getting good now. All right. So if r is the position with respect to time, then r double prime is acceleration. That is true. But what's going on here is, so with acceleration, it's kind of a more complicated beast, right? So those who had some ideas of why that vector was seemingly at different values of little t, it was pointing in very varying directions. So why? So yeah, Aiden.
Well, some of the acceleration is used to change the speed.
Right.
And then some of it is used to change the direction of the velocity.
Nailed it, right? Okay, so that's exactly right. So acceleration, there's acceleration due to like hitting the gas pedal, speeding up or hitting the brake, speeding up and slowing down. That's what we commonly think of acceleration. But then there's another reason for acceleration, and that's if you do what? You turn. If you're turning, you're actually changing speed in the n direction. So when you're turning, your speed is changing in the n direction. So there's an acceleration due to turning as well. Okay? So acceleration is due to two phenomena, speeding up and slowing down, which is in the direction of, what's that the direction of? Yep, and what do we call that going forward? Just the t, the tangent vector, right? And then turning, which is the direction of n. And it's really, we can say it's due to turning, but it's really due to speeding up and slowing down, but in orthogonal to t. That's what turning is. It's speeding up or slowing down to the side, right? Up. You're turning. Okay, I'll show you something next time. I'll show you that. Okay, so thus, so we want to separate out those two things, and then we can make sense of it. But just our double prime function, you see that picture that I just showed you, all those vectors, it's haywire, right? But if we separate out acceleration due to speeding up and slowing down, and acceleration due to turning, then the picture, we can make sense of it. It becomes more clear. So I just want to point something out. So we know what that is. That always has magnitude, what? 1. This is the acceleration due to speeding up and slowing down. Is that a scalar function or a vector function? That's a scalar function. So this is scalar multiplication of the scalar function of a tangential acceleration times the unit tangent vector. So all that together gives you what? If you put all that together, you would get what? A vector or scalar function? A vector function whose magnitude is what? It's the magnitude, has that magnitude, that tangential acceleration, and the direction is in capital T. So you put all that together and you get the vector version of that function, which includes the direction T. Same with this. So you put all this together. So this is the scalar acceleration in the direction of n. This is the vector in the direction of n. Multiply those out and you get the vector function for normal acceleration. So really make sure you understand what all those individual functions do, whether they're vector or scalar functions, and how that all works together. So review, when you're studying, what is that? What's the independent variable? What's the dependent variable? What do I get? Do I get a vector? Right? And then go through each one of these. Okay. So we want to figure out, so what we're after here is what is the tangential acceleration and the normal acceleration functions. We know what the t and the n functions are, so we want to figure out what these functions are. So we can do that by taking the derivative of the first derivative, right? The derivative of r prime. So r double prime is going to be the derivative of the r prime function. And how can we represent the r prime function? Well, it's really the speed times the unit tangent, right? So by v, I mean the magnitude of r prime. So I'm calling that the velocity function. That's the speed function. So now I'm taking the derivative of the speed times the unit tangent. What do I have to do the derivative then? Product rule, right? These are two functions of little t. So I need the product rule. So it's going to be the derivative of the speed times t plus the speed times the derivative of t. And so look, that we already pretty much have this, right? So we're going to have to do some rearranging, some pushing some symbols and substituting to get this. So if you remember, so this is kind of an aside. So recall that the curvature was the magnitude of t prime over the magnitude of r prime, and n was the magnitude of t prime over the magnitude of t prime. So we talked about that in the earlier class. So we're going to use these relationships to change this, right? So our goal is to get this to look like this. Do that in the video. So our goal is to get this to look like this. We're going to use these relationships and substitution to do that. Make this look like this. So here's how that works. So first I'm going to solve for this t prime, and that's going to be this magnitude of t prime times n. And then the magnitude of t prime is going to be the curvature times the magnitude of r prime. So then for the magnitude, for the t prime function, I get that right there. And we're going to substitute that in for t prime. So here we got lots of equations. We're rearranging and substituting, right? We're just rearranging and substituting things. So then we get this. So when I substitute that in for t prime, when I substitute this in for t prime, my first term stayed the same. Now my next term is the speed function squared times the curvature times n. And now, like I said, now it's starting to look like what we wanted, right? This something times t plus something times n. Now we're really getting close. So therefore, the real valued tangential acceleration is just the derivative of the speed. You knew that before you walked in the door today. And the real valued normal acceleration is the speed squared times the curvature. So here's an alternative way to find those. So this is an alternative way to find those. In a vector sense, right? So our functions will be given as vector functions. So rather than finding derivatives and magnitudes, and then like that, so we can do this. So the question is this the tangential acceleration? Is that a matter of dot product or cross product? So we want the part of the second derivative that's what? In the direction of r prime or orthogonal to r prime?
In the direction.
He wants in the direction. Agree with that? Right. Tangential acceleration. We want the part of the acceleration that's in the direction of r prime. Therefore, dot product or cross product? In as much as they're in the same direction is dot product. Dot product. So as much of the second derivative that's in the direction of the first derivative, or in the direction of t. That's going to be our acceleration, tangential acceleration. And then here's the normal acceleration. So the acceleration in the n direction, is that going to be as much of the second derivative in the direction of r prime or orthogonal to r prime? Remember, n is orthogonal to t. So we want as much of this as is orthogonal to r prime, and so that's going to be cross product. Now for all these, I should have a function of little t. These are all scalar function. This is all scalar function of little t. If I were to change the slide, I'd be a capital T of little t. This here, right? So when I'm writing just a sub t, I really mean that. And then when I'm writing just a sub n, I mean that. Not sure why I left the little t's off. So these are the, so in terms of calculating at and an, when you start with a vector function, these are going to be easier. It's an alternative way to get these right here. Okay? And then remember, so are these scalar functions or vector functions? Scalar. So if I wanted the vector function of a tangential acceleration, what would I do? Multiply that by the tangent vector, and then together that would give me the vector function of tangential acceleration, direction and magnitude. Same thing, if I want the vector function for normal acceleration, I'll take the scalar function and multiply it by normal vector function, and that will give me a vector function for the normal component of acceleration. Okay, any questions?
Why does it say R? Oh,
What's that? You
I
good?
thought it said R instead of R double prime.
You good? Okay. All right, so let's go back to our picture. And make sense of why the direction is flying all over the place now that we understand that. Let's just let it run for a sec here. Well, we want to make sense of the direction and magnitude of our gold acceleration vector at any particular time. So let's just. So why don't you guys talk about this? So I'll slow it down. I'll make it not so fast. And at different segments of this curve, try to based on what we just talked about, try to make conclusions about why is the magnitude and the direction of our gold acceleration vector what it is for different segments. So you could talk about maybe along this first segment here, along the loop, coming out of the loop, etc. I'll slow it down. And then you get a partner, and everyone's talking about this. So here's phase one. So talk about, this is kind of like section one here.
So it's like you're stuck between 0 and then you reach for the turn.
All right, so can you make sense of section one? Why is the acceleration pointing in the direction and has the magnitude that it does? Any thoughts? Yeah.
Because it's decelerating.
Slowing down, therefore? You mean so we're slowing down?
Yeah.
So we're slowing down. So what would that mean for the acceleration vector?
It would be in the negative direction.
Opposite of direct, right. So because it's slowing down, it's kind of pointing in the backwards direction. Anything else about this? What's the other aspect to acceleration? Yeah, so what about turning here? Okay. But most of the acceleration is due to what? Most of the acceleration is due to slowing down. Is there much turning?
You have to slow down half a turn.
Just a little bit of turning. So you have a little bit of effective turning. That's why it doesn't look like this. What would it look like if there were no turning? It'd be straight back. If there were no turning, it'd be like this. But there's a little bit of turning, so therefore the direction of turning is down. So there's a little component of turning, but most of the acceleration is due to slowing down. So those two together give you the current acceleration vector. Okay, what about on the loop? This is cool. What about on the loop? What's happening on the loop? Orthogonal, pretty consistently. Why? All right, it's turning the entire time, but then also staying at a pretty constant speed, right? So if it's staying at a constant speed, then what's our tangential component? The tangential component? 0, right? The tangential component would be like in the direction of the blue vector. If it's staying at constant speed, going forward, then we're not going to see a component, and then the acceleration will be pointing in the direction of turning like the whole time, if it's staying at a constant speed through there. Does it make sense? All right, what about coming out of the loop here? So what about right now? Speeding up. Going straight, no turning. So then it's going to be right in the direction of the blue one. So we've got all tangential and no normal component of acceleration here. So cool. And then what about now? Consistent speed, but turning down. So all of it's in the normal direction. All the acceleration's in the normal direction. But that we can kind of conclude that it's kind of at a consistent speed here because we don't have a component in the direction of the tangent. Okay, what about in the back? What about back here? Speeding up, that's it? Mostly turning or mostly speeding up? Mostly speeding up, a little bit turning, right? So you have a little bit turning downward, most of it speeding up in the direction of the blue. Right? So the acceleration vector, this r double prime, is the sum of two components of acceleration. And so then as your speed and your direction is changing, you get all kinds of combinations of that. And that's what we saw in the original when we watched it for this vector. But now, understanding how it's broken up, we can really make sense of the direction of magnitude. Okay, any questions on acceleration? All right, so we're going to change gears and stop talking about vector functions for a while and talk about something called multivariable functions. So it would not be wrong to call this a course in vector calculus, but it also would not be wrong to call this a course in multivariable calculus. So we're going to talk about multivariable functions. And then the end of the course, we're going to be doing it all together. Everything that we've learned throughout the whole course is going to be participating in what we're learning. We're involved. Let's see, so where do I want to go here? Okay. So multivariable functions. So we're kind of changing gears here. So most functions you've encountered are of this form. Y equals f of x. Is it real valued or vector valued function?
Real value.
And real value is pertaining to x or y? He wants x. When I say real valued function, that's talking about x. Is that right? Y, right? The dependent variable. So y is the real value that's referred to as a real valued function. Okay? And so and we're going to take this a step further. Besides a real valued function, it's also a single variable real valued function. Single variable is referring to the x or the y.
X.
That's the x, right? There's one independent variable, that's x, and then the function gives us a real value, and that's y. So this is a single variable real valued function. Okay, so let's practice here. What kind of function is this? Is it single variable or multivariable? Single variable, which is t, and then is it real valued or vector valued? Vector valued. Single variable, vector valued function. That's our space curves, right? So what would a multivariable real valued function be? What would a multivariable real valued function be?
A sphere.
What's that?
A sphere.
Well, that might be an example of it, but in terms of what do we mean by a multivariable real valued function? Multiple independent variables. So like f of xy or xyz or xyzw. So more than at least two, right? At least two independent variables. And then what comes out of that? A vector or a value? Just a real value. And so our most basic multivariable real valued function will be z is a function of x and y. But w could be a function of x, y, and z. That would also be multivariable real valued. Okay? W was a function of x, y, and z. But we're going to start with the most basic kind of these, which is z is a function of x and y. So here's a nice example, wave height. Wave height in the ocean is a function of two things. It's a function of, it depends on the wind speed and then how long that wind blew for. So I wish I would have got the video. It was at Rocky Point a couple years ago. And by 4 p.m., the waves were so high at our resort where we were staying. I mean, they were like 8 and 10 feet tall, these waves. And it was because the wind was blowing hard all day long. The wind has a high velocity and it was sustained. And so if you have a calm ocean and you have just a gust of wind for a minute or 30 seconds, you're gonna have big wave heights? No, you might get a little bit. But if you have that same wind sustained for 30 minutes, an hour 30, then your waves are gonna start growing, right? So you see how the resulting height would be both a function of the speed and then how long the wind is blowing at that speed. Good example of a multivariable real valued function. Okay, so we want to talk about, there's 4 ways that we represent these, right? These multivariable functions. 4 ways to represent them. And the first is a formula or a function definition. So we talked about z equals x squared plus y squared. What was that? Remember?
Circular parabola.
That was our reference circular paraboloid. It was like our basic circular paraboloid, right? Well, now we could change that up to the z values being like our dependent variable. So you could use f of xy. And so this formula, or this function definition, f of xy equals x squared plus y squared, is one representation of that multivariable function. And so how do I represent the value of z when x is 1 and y is 2? Am I asking you to do the math? Am I asking you for 5, the number 5? I want you to represent, what's that? F of 1, 2. That is not a command for you to do something. And that's maybe how you've seen that in your whole math class. Oh, I know what that means. That means take 1 and plug it in, take 2 and plug it in, and calculate a number. That's not what that means. What that means is it just simply, it stands for the value of z when x is 1 and y is 2. Regardless of whether we calculate it or not, it still has that meaning. I can use that representation in other equations, in expressions, to represent that value. You don't have to find it. This is not a mandate, right? It's not a mandate for you to find that the value is 5. Now, if you wanted the value, you could find it, and it is 5. But by itself, it's perfectly content to stay looking like that and not be calculated. Okay? So this is the first way to represent multivariable functions is using a definition. And then with definition, we have this very, very powerful tool of function notation to represent values of the dependent variable. Next way is a graph. A graph in R3. So before, with our graphs of y equals f of x, we had our independent variable x, and for any given value of x, the dependent variable was represented how? The corresponding value. How is it represented in the graph for different x's? Ali, how is the value of the dependent variable represented for different x's in the Cartesian plane? Right, the corresponding y value, which is like height above the axis, right? So for any x, there's a corresponding y, and that is like the height above or below the x-axis, right? And then if you let x vary continuously, you got a graph, right? So what is it in R3? What is our independent variable? Two things. So x and y, right? So combinations. And where do those live? In the xy plane, we're going to get ordered pairs of x and y that together give us those are independent variables, and together give us an ordered pair, which is like a starting point. And then, for every ordered pair x and y, the dependent variable is represented by height, z, up or down. Still up or down, but now those up or downs are z's. So when I first introduced the R3 coordinate system, it seemed kind of weird. Why didn't x go up and y go to the right and z come out at you? That would be kind of intuitive. But it's because of these. It's because of these multivariable functions. We want our independent thing to be in the horizontal plane, and we want dependent to still be height, right? So we still want z to be, or the dependent variable and the quantity to be up or down. And so then our launch pad for our independent variable is now the plane, the xy plane. And so if we get a point for every xy ordered pair and we put all those points together, what kind of thing do we get in general? We put for all xy ordered pairs, we have a height, and we put all those points together, those ordered triples together, we get what kind of thing? Surface, right? Surface, which we know this is our circular paraboloid. This is an example. So we get our surface. So the graph as surfaces. And so all those surfaces that we've learned so far, now we can think of them in the light of a multivariable function, where z is the value of the function for given combinations of x and y. Our resulting values of the function are z. So then those surfaces are like our curves that we've thought of before, y is a function of x. So we know what this one looks like, right? Vertex is at? Yeah, so when x is 0 and y is 0, the value of the function is 0. And then we know how this goes, right? So all the z values will be positive. We're summing two squares. And this thing looks like this. Circular paraboloid. But now we're seeing it in the light of a function rather than just a surface, right? A function meaning for any xy, there's a corresponding z. And then the order triple is a point on the surface. So x, y, f of xy. As our order triples on the surface. Okay, now we talked about level curves. So let's look at this. So remember, for that paraboloid, we took what? Constant values of z, and we plugged them into our equation, z equals x squared plus y squared, and we graphed those in the xy plane. So z equals 1 gave us the unit circle, right? Z equals, here's 3, gives us a circle of radius square root of 3. And so for every z value, remember we did these traces that we called level curves. So here's z equals 7. There's c equals 8. So if we were to graph all of those at once, so say it's first c equals 1, 2, 3, 4, 5, 6, 7, 8, it would look like this. So graph a bunch of level curves for this equally spaced z values. That's key. So we want the z values to be equally spaced, and then graph all of the level curves in the xy plane. That's a representation of the same function, z equals x squared plus y squared, because we have ordered pairs x and y, and then these red, the red level curves tell us the corresponding value of z. So you've got the function, right, for every xy. a corresponding z. So notice what the circles are doing. They're spaced further apart here and then closer and closer together. How does that give us a picture of what the surface is? Brian?
As they get closer and closer together, the components are closer to each other. If they're spaced apart more, then they're further apart.
Okay. So the z values, so the z values of these level curves are constantly spaced. The z values, it's the same. I think these are all 0.5 away. So this is z value like 0.5, 1, 1.52, 2.53, 3.54, 4.5. So the z values of the red level curves are in equal intervals of z values.
That means the steepness of your curve is getting more steep because even though your z values are still the same amount apart,
Yeah.
your radius it's not increasing as much. So your circles are not getting smaller, but they're not increasing as much despite the fact that it's still going up at the same rate.
Okay. You already said? Yeah, so down here, so for the change in z, so for a big change in x, y, we have the same change in z as here. For a smaller change in x and y, we have a bigger we have the hard to explain. All right, so for the same change in all right, so I got it. So here, if we change from here to here, we have a certain change in z, and that was for a change of what, 0.5. Now, if I go from here to here, it's also a change of 0.5. What was the change in z now? How does the change in z from there to there compare to the change in z from there to there? Much more greater change in z, right? Because I'm going across lots of these level curves. That means the surface is much shallower here than it is here. It's much steeper here where the lines are closer together. Yeah?
How can you tell like what direction it goes? Will the z values be given or like?
Yeah, so for this one, like I told you, right, so you're right. So like going out away from the origin, those z values could be going down, right? Yes, so you have to be given some numbers. So each one of those curves is a constant z value. So I'm telling you that this one's 0.5 and this one's 1 and this one's 1.52. So z is increasing away from the origin. So you'd have to be told that. Okay, so we show them all here. I think this shows them all. So you put all those curves in the xy plane. So those are all level curves on the surface. You put them all in the xy plane, it looks like this. And so this is called a contour map. It's like a topological map. You guys ever hiked or done anything like that? You've used a topological map. It's called a contour plot. And it's just like a topological map. Stay on the curve, you're staying at a constant z value. Move from curve to curve, you're changing your z value. And if your curves are close together, you're changing steeply, right? Because for the same distance in the xy plane, your z changes much more than, say, when the curves are far apart. So this right graph is a representation of our multivariable function. You can get values of z for any ordered pairs x and y in the plane. Okay, so the traces equals k for various k's. Those various k's have to be at equal intervals. So that's key. I should have put that. If those lines are not at equal intervals of z, then you don't have you don't really know. It's very hard to make sense of what's really happening. Okay, and then The last one, which is pretty easy, table of values. Pretty kind of boring, but it's still a valid. Boring, but we do see them in application, so we got to be on the lookout. So, say -3. So when y is -3 and x is 0, z is 9. Then 10. That's not y to the -3. These are y's. There we go. All right. Say when x is 2 and y is -1, then we get 5, right? And when they're both 1, we get 2. And when x is 3 and y is 0, we get 9, etc. So we could fill that table in. So these are the z values corresponding to ordered pairs of x and y. So a table of values is another way to represent multivariable function. So these are the 4 main representations. A definition, function definition, a surface in R3, a contour map, which is in the xy plane. It has the traces of z traces at equal intervals, and a table of values. So let's just go back to the contour map. That's the most unfamiliar thing. I'll give you one more practice problem here. So here's a contour map. And I'm giving you, this for point 4, 1. So along the actual x-axis there's a trace at 1. Here's 2. Here's 3. Okay. So these are spaced at, what are they spaced at? Point 2. All right. So see if you can sketch the surface and maybe try to come up with what function this is based on this contour map. So talk amongst yourselves. We got a minute. What happens to z values as you increase in y? What happens to the z values? No, just the z values. Just as you increase in y, what do the z values do?
0.
Right. They go down, and it seems like they're approaching 0, right? And as you increase in x, what happens to z values? Stay constant. So what would that be? As you move in the x direction, you're going to stay at constant level. As you move in the positive y direction, you're heading down and approaching 0. And how are you heading down? First, you're heading down steeply, and then as y increases, you're heading down less and less steeply. Can you imagine that surface? What is it? Exponential? Good, it's an exponential cylinder. It's a cylinder because in the x direction you stay constant, right? So this is the exponential cylinder. What might the definition be? That you would decrease as y increases. Z would decrease as y increases. Anybody? You want z equals e to the negative y. So the most important thing is that was the surface you imagined after looking at this contour map. And so representation, so here's 3 representations. F of xy equals e to the minus y. It's an exponential cylinder. You've got the surface in R3 and then the contour map in R2. 3 different representations for that same function.